This is a type of game that was very popular in Norway 40-50 years ago. It's a coin-operated game where you play using Norwegian 1 kroner coins. The aim of the game is to hit one of those targets. If you hit the number 7, the game pays out 7 coins. If you hit the number 3, it pays out 3 coins. Or if you miss the target, you lose your coin. There you go. The game should have backlighting here, and it should also indicate the score with a 7-segment display here. Unfortunately, this game is no longer working, but we can take a look inside to see what should be going on. So this is what the game looks like on the inside. Behind each target there is a micro switch. So if you hit one of the targets, the coin will trigger the corresponding micro switch. The coin will exit here and trigger this switch, indicating that the coin is coming through. This chute will feed this tube. This tube again feeds a disc that holds up to 4 coins. If you hit one of the targets, the game controller will release the brake on this AC motor, and the motor will start spinning. The disc can hold 4 coins. So for each quarter of a rotation, it will pay out 1 coin. And for each quarter of a rotation, it will trigger this switch. So the game knows how many coins it has paid out. It also keeps track of the number of coins that has been spent on the game and the number of coins that the game has paid out. So if we look at this game has seen 329,200 Norwegian kroner, and it has paid out 273,796 kroner. So that was a decent amount of money. If we'll take a look at the electronics, we have 2 printed circuit boards. This small board here has a 7-segment display on one side and some electronics for controlling the display. And that connects to the main board, which handles all the logic. None of these boards are working right now. I made, maybe 10-15 years ago, I made this replacement board that slots into the same edge connector and also interfaces to the display board. That worked for a while. I made several of these and I haven't gotten any complaints yet. Until stuff started arcing underneath here. That fried my last remaining replacement board. And one option would of course be to try to repair the original board. But this is old, this is really old. It's handmade. As you can see, every trace is hand drawn on the board, probably etched at home. And some of these parts, you're not able to get them. And since my replacement board design is quite old, I was thinking maybe I should, instead of trying to preserve backwards compatibility, using a really dangerous edge connector where you have signals from switches and 230 volts on the same edge connector. Try to rewire the game to operate on 12 volts, which is a much safer voltage. So another really annoying thing about this game is the way the switches are wired. You have separate signals from the number 2 payout, 3 payout, 4 payout going into the controller. But the number 7 payout you have to treat differently. So you have to, in order to pay out the correct amount from the game, you have to look at both the switch state of the number 7 and the other switches. And since these switches are quite old and they're really, really bouncy, debouncing is hard. It's really hard. My plan is to convert this to 12 volt operation. So I'm going to rip out the fluorescent tube stuff. You can't get those tubes anymore anyway. I'm going to rip out this. I'm going to rip out this, and the 230 volt motor. Probably make a new wiring harness and a much more elegant board. I'm also going to make a board that has Wi-Fi or Bluetooth connectivity, so you can keep track of coins in, coins out on a separate backend somewhere in the cloud. So, time to get destructive. Wiring harness gone. Fluorescent tube gone. Replacement board gone. Display board gone. Motor to be decided. Power supply gone. So, time to get to work. Let's take a look at the schematics for this thing. So the board is going to run on 12 volts via this connector, and the reason for the 12 volt power supply is that I can use the same power supply for providing power to this board, and I can use the same power supply for providing power to a LED strip that can replace the existing fluorescent tube that provides backlighting to the game. I'm using a TPS62172 buck regulator that can accept anything from 3 to 17 volt input, and it will give me 3.3 volt output, and it can deliver 500 milliamps, which should be enough for powering everything on the board. This is the power connector, and these three are LEDs
for showing that I have 3.3 volt USB voltage and 12 volts present on the board. This is the sheet for the USB and the microcontroller. So I'm using the CP2102 for connecting the board to USB. And the output from this CP chip is mapped to the RxD0 and TxD0 pins on the microcontroller. The first GPIO pin, IO0, is mapped to this button, and that's for enabling the bootloader mode. So if I press this button and apply power, it's possible to flash the board. IO pin 1 through 7 are input pins. Those are mapped to the hopper switch, coin exit switch, payout switch 2, 3, 4 and 7. And IO pin 8 through 12 are output pins. The first 4 are mapped to the BCD decoder. And the last one is mapped to the relay. And this is a representation of the terminal block for the input switches. And this is the kind of main decoding for the BCD, or the display that's supposed to go on the back of the board. So we have 5 signals coming into ULN 2003 transistor array. First 4 are BCD signals, and the last one is for the relay. So I'm cheating a bit here, because the CD4511 BCD decoder runs at a higher voltage than 3.3 volt. So I'm pulling all the inputs to this decoder up to 12 volts, and I can pull them down via the ULN 2003. So the effect here is that I'm inverting the logic here, but that's easily handled in software. And this BCD decoder has one output for each segment in the 7-segment display. Yeah, and this is the representation of the relay. I could potentially just hook up the motor to a connector like this and provide power to the motor via the board, but it leaves more options open if you can connect a power supply in series with the motor and connect this to the relay. And that means that you can use a 12 volt motor, or you can potentially use a higher voltage motor on the same board, so you have more options open. Yeah, this is just a print of the PCB itself. So it's a 4-layer board. I have routing on the top layer and the bottom layer, a 12 volt power plane and a ground plane. So yeah, that's the board. Hi again, it's time to jump into the code. So I've already written a piece of code that yeah, this is the test harness. It's just the buttons, or these represent the switches in the game. This is the display, and I have some simple logic for detecting button presses. So this is the 2 payout, 3, oops, wrong way, 4 and 7. So now I'm going to do the payout routine, so we can take a look at what the code looks like. I have a truth table for the BCD decoder here. This is inverted, since I'm doing a little trick with a ULN 2003 level shifter, or transistor array that acts as a level shifter. We have some GPIO definitions. The output pins are mapped to the BCD decoder. These are the input pins. So from the hopper switch, coin exit, payout switches. I also defined, so this is the kind of function for displaying a digit on the display. So I select the GPIO BCD base pin number, and just
look up the truth table and set the corresponding pins. These input pins have been hooked up to interrupt routine. So when you press a button, I get an event, and I map the button number and also the timestamp for when it was pressed, and just stuff it into a GPIO event queue. I have a GPIO task. It runs forever, just reads from this queue, and then it checks the timestamps of the events. So my approach to debouncing here is that I detect all the bounces. I detect if I get multiple events on a key press, I eat all the events, and I just check the timing up against my debounce limit. So if the timing since the last press of a certain button is greater than my debounce limit, I'll process the event, otherwise I'll just ignore it. So these are kind of empty so far. I'll just print out what's happening. Welcome message. This is the main function. I initialized the SPIF's file system. I'm going to stuff some certificates in there eventually. Initialize GPIO, and I create the GPIO task. Then I add a handler for each of these button presses. And then the code just prints the welcome message and runs in an infinite loop. So what I'm going to do now is I'm going to add a payout task, and that means I have to define some semaphores in order to synchronize these two tasks. So we'll start by including the necessary include file. So we have to include free artos semaphore. Whoops. And we have to define our semaphore. Do that here. Semaphore handle type X. Let's go payout semaphore. And we also have to create an instance of that semaphore and do that here. Semaphore. That's of course. Let's create semaphore right. X semaphore create binary. And we need to define our task. We can do this here, maybe. Static void payout task. I'm not going to do anything in this task yet. I'm just going to verify that it's running and that I can take the semaphore. Running. And this will also run in infinite loop. For take payout semaphore, and this will block from eternity. So we'll use port max delay. I'll just print out the statement saying that I've successfully taken the semaphore. Send taken to Yeah, and we also have to create that task, so and start it. So start task create task stack size. Let's see if this compiles. Yeah, compiled. So now I can try and flash that. I think this should appear as comport 5. Flash comp5. Yeah, it's flashing. Ah, I forgot something. Of course, I have to give it a semaphore. Let's test for the 7 payouts. Semaphore give x payout semaphore. Okay, let's start again. Build. Flash it. Confirm. Okay, now it's flashed. Let's see the monitor. It's not crashing, that's a good sign. So if I press the button, okay, 2. If I press the number 7, we should get the semaphore take-in message. Yay! So now I only have to implement the motor routine. Okay, finished soon. I won't be able to fit everything into one video, so you can consider this part 1 of a 2-part series. In part 2 I'll hopefully have finished the code, which is like 95.5% finished by now, ish, kind of. I'll also replace this monstrosity with a 12 volt version. This is a 12 volt geared DC motor from China. I'll use this 3D printed adapter plate. And I'll also have to make a brand new wiring harness. I'm really looking forward to that. Yeah, and I need to add 12 volt backlighting. I'm going to use a cheap LED strip, I think, and find a suitable power supply. Yeah, as a final exercise, I'm going to hook this up to our IoT backend. It's a thing, it's connected. And since we're living in the IoT age, or Internet of Things, it has to be connected. There's no other way around it, according to Gartner. Okay, we'll see you next time. Bye.